All right, so up until this point, we've talked about situations where we said the reflux to the column was being presented as saturated liquid reflux. Right, today we're going to talk about subcooled liquid reflux. This is something that often occurs, or is often something that is used from a practical perspective, because returning or pumping saturated liquid reflux is somewhat problematic. So if we think about what happens in a particular specific application of a distillation column, right, it's unlikely that we're going to build the condenser, 50 or 100 or 200 feet up in the air at the top of the column, right? In principle, the condenser is most likely going to be positioned down at ground level, and will basically have an overhead pipe that brings the vapor off the top of the column down to ground level where it is condensed in the condenser, and then we pump that liquid back up to the top of the column where it re-enters as the reflux. And so if you think about the situation there, this idea of trying to pump a saturated liquid is problematic because the pump can create or pull essentially some sort of vacuum as it's turning. And if you have a saturated liquid, that decrease in pressure at the inlet for the pump can cause vaporization of the liquid, or what's typically called cavitation in a pump. And cavitation can literally destroy a pump. And so we don't want to have cavitation occur, and so oftentimes we try to avoid pumping saturated liquids. This just means in this situation that we're going to have a situation where we're going to be thinking about trying to analyze the problem that comes up as we think about a situation where we have a subcooled liquid reflux. And so again, all the subcooling means is just we are at a temperature that is lower than where we would be if we were on the saturated liquid line on a TXY diagram, for example. And so what we need to do is we need to think about how this influences then our internal balances in the column. Right? This is going to be very similar to dealing with a subcooled liquid feed to the column, right? Where we've seen some examples about how as you bring a subcooled liquid feed into the column, we have to condense some of the vapor in order to make up the enthalpy difference between the subcooled liquid and the saturated liquid that's in the column. And this is going to be the same situation here. We're going to have this situation where some number of moles per hour of vapor is going to be condensed, and that's represented here by C. And so we see that here, and this is going to be what we're interested in thinking about as we look at subcooled liquid reflux. And so what we're going to do is we're going to do some energy balance analysis, but essentially we'll show that C can be related to or at least is approximately equal to, under assumptions related to CMO, to the enthalpy difference of the saturated liquid and that of the reflux, right? So we're expecting that saturated reflux, the reflux that's coming back to the column is subcooled, and so that enthalpy is going to be a little bit less than the H liquid here, which is the saturated liquid enthalpy. So we're expecting to have a situation where we have some number that's greater than 0 here in the numerator. And then that's going to be divided ultimately by the latent heat of vaporization, right? And so essentially what we're saying here is that somehow we have to satisfy this energy balance where we have to make up for the difference in the reflux enthalpy in this subcooled liquid reflux case relative to the situation that we have for the saturated liquid. We need the latent heat of vaporization information to do that. And if we have that information, then this gives us a factor that we're going to call F sub C that describes essentially how much we're going to have to steal from that vapor stream to make up this energy balance. And ultimately what's going to happen, right, is you see that this disrupts the way that we would do the top operating line analysis, Right now, instead of saying that the top operating line slope is L0 over V1, we're going to have to consider it to be L1 over V2. And under the CMO assumptions, then we would proceed with L1 over V2 being equal to L over V, which is the top operating line slope. But that internal reflux ratio is going to be affected by this introduction of subcooled liquid reflux. And so we need to think a little bit about how this enthalpy balance works, and we'll talk a little bit more in class about how we use our material and energy balances to make some sense out of this. But before we get there, we want to think more about this physical picture and what's actually going on in the column, and why it makes sense that we have this situation where the subcooled liquid reflux has to steal some of the vapor and condense that out to basically close this gap in the saturated liquid enthalpy and the reflux enthalpy, which is embodied in the numerator of this F sub C parameter.